Good afternoon. We are going to be taking notes on Chapter 3, the first day, INQ Point 1, real numbers and interval notation. Some of what we cover will be review, others will be new. One page I'm going to be using is properties of exponents. So if you want to print that out and include it as part of your notes, you can. Or when we get to this section of the video, you can pause the video and copy down the algebraic properties so that you have them to refer to. Real numbers and interval notation. Okay, Roman numeral 1. We're going to start with interval notation. We've done a little bit with interval notation, but now we're going to expand what you know. Okay, so part A, endpoints. Okay, there's two types of endpoints in interval notation. The first type of endpoint are brackets. And when we refer to brackets, we say that the endpoints are inclusive, because they are part of the solution set. Another term is closed. They are closed because they are part of the solution set. And again, most important is the endpoints are part of the interval. This is a lot like when we do filled in dots on open or closed dot graphs. It's pretty much the same thing. All right, so we're going to draw a couple of little number lines, not very long. Okay, so on the left, this is the old notation that you're used to using. And in the old notation, let's say that x is greater than 2, greater than or equal to 2, and less than or equal to 5. So 0, 1, 2, 3, 4, 5. Switch pens. So in the old notation, we would use a filled in circle to show that 2 was part of the interval and 5 was part of the interval. That's your old notation. That's called inequality notation. So if they're asking for inequality notation, this is what they want. Now, the new notation would show the same interval, but with a bracket on the 2 and a bracket on the 5. It's shorter, easier to write, a little more concise. So let's mark this out. 1, 2, 3, 4, 5. So you end up with a bracket on the 2 and a bracket on the 5 and a line in between. Notice the brackets are facing each other. And it means the exact same thing, but this would be interval notation. And that's what we learned to use in pre-calculus, and it's primarily what we use in calculus. All right, so that is the first type of endpoint, inclusive or closed. Now we're going to go on to the second type of endpoint, which is parentheses. And these are referred to as exclusive endpoints or open endpoints on an open interval, which basically means the endpoints are not part of the interval. So endpoints are not part of the interval. Okay, and like before, we're going to do a little comparison here. So draw yourself two small number lines. Okay, so in the old notation, you might have something like x greater than 0, less than 3. And on the graph, 0, 1, 2, 3, we would have an open point on the 0, an open point on the 3, and a segment in between. In the new notation, the same interval would be written 0, 3 with parentheses around it, and we would have a parenthesis on the 0, a parenthesis on the 3, and a line connecting them in the middle. Now you might say, hey, that looks like a point. How do I know it's not a point? Context. I wish I had a better answer for you, but it's context. What are you working with? what is it that you're dealing with. That's the only way to tell the difference, because they do look very similar. Okay, part 3, combinations. Combinations are where interval notation really starts to shine, because it is so much easier to represent things for a combination using interval notation. So we're just going to do a big example here. So draw a really long number line this time. And our first critical point will be -4, 3, 2, 1, 0, 1, 2, 3, 5, 6, 7, 8. Those are going to be the critical points on this. So what we're going to do is take an inequality graph of a number line, and we're going to turn it into interval notation. So let's put it on here. We have an open point at -4, and we have a closed point at 0, and then 3 to 5 closed points on either end, and then 8 has an open point with an arrow going to the right. So our solution set, or our set of x values, are on 3 different intervals. So this is where we're going to use interval notation to represent each piece. So this segment from -4 to 0, -4 has an open circle, so it's open or exclusive. It would get a parentheses. Up to, now 0 is filled in, so it is closed or included, so it gets a bracket. Now the symbol to tie these together is a union symbol. It looks like a U without the stem on it. It's actually a Greek symbol. Now 3 and 5 are both inclusive endpoints, so they both get brackets. 3 and 5 in union with. And our last one starts at 8, exclusive, so it gets a parentheses, and it goes to positive infinity. Now whether you're going to positive infinity or negative infinity, it always, always, always gets a parentheses, because infinity never ends. It just keeps on going. All right, so that is our endpoints that we're going to be working with. All right, let's go on to boundaries. So part B, boundaries. Now there are different ways to describe different types of intervals. Like always, we need a math language so that we can communicate what we see. I'm going to give you 5 different types of bounded intervals, and we're going to describe them. So here we go. Number 1, AB. If both A and B are in parentheses, we call this an open interval, because it is open on both sides. Number 2, if A and B interval is bracketed, we say it is a closed interval, because both ends are closed. Now I want to pause a moment. I've just used the words open and closed to describe 2 different things, and I want to make sure you notice that. An open endpoint is the B. A closed endpoint is this B. So you can use open and closed to describe an endpoint, but you can also use open and closed to describe the entire interval, which is what we're doing here. Okay, number 3. This one has a closed on the 2 and open on the 5. They call this a half open interval. Half open. All right, let's say you have a negative infinity up to a 2. With negative infinity on one end and 2 on the other, the interval is named for the endpoint, not the infinity. So the fact that the 2 is an open endpoint means the whole interval is an open interval. And again, that's because of the 2, not the infinity. Last one, bracket on 3 to positive infinity. Again, you name it by the endpoint that is there. The 3 is closed, so this is a closed interval. And again, I'm going to draw a little arrow. It's named after the endpoint that we actually have. All right, part C. We are going to describe intervals. We need to have some vocabulary to talk about what types of intervals we're working with. So we're going to describe intervals. So for example, if we have the interval 3 exclusive, 6 inclusive, the words we would use is all values greater than 3 and less than or equal to 6. And you can put or equal to in parentheses in a comma because it is a prepositional phrase. Here's that. All values greater than 3 and less than or equal to 6. So that's pretty straightforward. Boundaries. When we talk about boundaries, this interval, the lower boundary, has a parenthesis, so it is open. It is also exclusive. We say it's an open or exclusive boundary. For the upper boundary on our example is the 6. This is a closed or inclusive boundary. And you could also say closed or inclusive. You could put the word upper in here or lower in here, depending on how the question is phrased. And the type of interval that you're dealing with. Well, one side is open, the other side is closed, so the type of interval is a half open interval. So on your homework, they're going to ask you to describe intervals using words, boundaries, and the type of interval. And that's how you go about doing that. Okay, part D. Bounded versus unbounded. We haven't really used bounded and unbounded terminology yet in reference to number line intervals. So bounded versus unbounded intervals. Okay, so a bounded interval, the definition is basically that it has two endpoints of any type. So, for example, 210 is bounded. Another example would be if there was a bracket on the 2. It doesn't matter if they're both brackets, both parentheses. I guess for the sake of completeness, we can put a double bracket here. They all have specific endpoints, so those are considered bounded. Now with unbounded, it only has one endpoint, and the other one is either a positive infinity or a negative infinity, one of the two. So an example of that would be 2 to positive infinity. Another example would be negative infinity up to 4 with a bracket. On the graph, an unbounded interval is one that has an arrow shooting off somewhere, whether it's right or left. Whereas a bounded interval, the graph will always have brackets on both sides. Okay, so now we're going to get to properties of exponents, which we always need work on. So this is Roman numeral 2. Again, if you don't have a printer to print this out, pause the video, take a moment to write down the properties of exponents. This is part 2, properties of exponents. And we're going to do a little practice with properties of exponents. Again, if you don't have it printed, take a second, pause the video, write it down. All right, number 1. Negative 3 squared. And I'm purposely going to make number 2 negative 3 squared because I want you to see the difference. basically, I'm going to show you why these are different. On the top one, a -3 is almost like a -1 times a 3, and it's being squared. And so using your power of a power rule, it becomes -1 squared and 3 squared. The -1 actually squares out, so you end up with a +9. Now on this one, the -1 is not being squared. Only the 3 is being squared. So the -1 is unaffected when the 3 becomes a 9, so the result is a -9. These are very easy to mix up, so I wanted to put them side by side for you. Okay, example 3, 2fg squared times 5f squared g cubed. And just for the sake of interest, I'm going to put a 2 out here. All right, so when you're attacking a complex situation like this one, you want to remember your order of operations. Look inside the parentheses to see if there's anything you can do. In this case, you cannot. Now here's where the kicker comes. In your order of operations, it goes grouping symbols, exponents. So this exponent takes priority, and that's the one you're going to do first. So we're going to use power to a power rule, and what I find is people forget that the 5 has an invisible power of 1. So when you distribute the 2, it actually needs to get distributed 3 different times. I'm just going to rewrite the 2fg squared. So when you distribute that, you get 5, and then it's 1 times 2 is 2, f to the 2 times 2, which is 4, g to the 3 times 2, which is 6. That's your power to a power rule. Now that we've done the exponent, we're ready to go to the product. You multiply or divide, so we're going to multiply those two together. So product of power rule says keep the base, add the exponents. Remember that f has a power of 1. Now, product of a power rule doesn't affect the numbers. So we still have a 2 times a 5 squared. They don't change each other, but we have f to the 1 plus 4, g to the 2 plus 6. Simplifying further, 5 times 5 is 25, times 2 is 50, f to the 5th, g to the 8th. And that is your answer. All right, number 4. U cubed v to the -2 over u to the -1 v to the 4th. Now there are 2 ways you can attack this one. You can move the negative terms, move the v squared down, move the u squared up, or you can use our division rule, power of a quotient, quotient of a power rule, which is the second one from the bottom. I'm going to use quotient of a power rule just to show you how it would work. So with quotient of a power, you keep the base, and then it's top minus bottom power. So for the u, it's 3 minus a -1. For the v, it's -2 minus 4, and that's all over 1. Negative times a negative is a positive, so I have u to the power of 4. -2 minus 4 is -6, so v to the -6. Now, you cannot end with a negative exponent, so you are required to move the v. So the v to the 6 moves to the bottom. You've moved it, so the negative disappears. Sorry, these are getting a little crowded. There you go. All right, last one, and then we're going to wrap this up. Example number 5. We're going to do 4x cubed y squared to the -2. If you think you've got this, pause the video, work the problem out, and then restart it and see if you are correct. So first thing I'm going to do is distribute the -2. Remember, the 4 has an invisible 1, so the -2 is going to get used 1, 2, 3 times, and it will be multiplied. So we have 4 to the -2, x to the -6, y to the -4. Now all of these are negative, so I'm going to move them down. There's now a 1 up there, and I have a 4 squared, x to the 6th, y to the 4th. No more negative exponents. Last step is to square the 4. 4 times 4 is 16. So 16, x to the 6th, y to the 4th. And there we have it. I hope you enjoyed the notes. It's an interesting section of the book. Have a good afternoon.